Now we come to the part of the course, the part of the handout, the part of Chapter 2 that ties all the abstract things together. So remember where we've been. We first talked about vector spaces, abstract topic, but we brought it back around to how do we represent a vector? We represent a vector, an abstract concept, in terms of coordinates, which are a nice concrete set of numbers. The coordinates, which were linear combinations of a basis. And so every vector has a unique representation in terms of a basis. And the basis, we can always change the basis, but it's also unique in that, or what is also unique is that a basis has the same number of vectors. No matter how we change the basis, it's always the same size, which we call the dimension. And then we went to linear transformations, which were also abstract. They apply to matrices, but they apply to derivatives and integrals and polynomials and all sorts of other things that come up in math. But as abstract as those were, we could still represent them concretely as a matrix. And so now we bring the concepts of vector spaces and matrices together in a different way, and this is also going to remind us of some things earlier in Chapter 2. Earlier in Chapter 2, we talked about two good ways to represent subspaces. One way was as a combination of columns, or as a combination of vectors, and that was related to the concept of span. We talked about a second way, which was as solutions to linear equations, and that was very much related to null space. And when we row reduce equations, we are eliminating dependencies. So this will have something to do with some of those things. We have the range of a linear transformation ends up being a subspace. The range of a linear transformation would be the set of all w's, the set of all possible outcomes. When we talked about the column space, or whether or not w would be in the span of a set of vectors, or in this case, the output of a linear transformation, all of those concepts had to do with existence. Does there exist a v such that w is achieved by the linear transformation L? And so the range is something else that we also learned way back early on in an algebra class. We talked about the domain of a function and the range of a function. The range is the set of all possible outputs. So now that we're in a little bit more grown-up of a class than those beginning algebra days, we have to realize that the range is not w itself. We talk about a linear transformation goes from v to w, but not everything in w can be achieved by L. And so w is not the range. The range is a subspace of w. So the range is a subspace of w. W is called the codomain, which is a topic or a word that seems to be left out of a lot of the basic algebra books. There's domain and codomain. Everything in the domain gets acted on, but not everything in the codomain needs to be achieved by a function. So the range is what is achieved by the function, a subspace of the codomain. The other one of these is the null space, which is the set of all v's such that L of v is 0, or the set of all possible inputs that just get mapped to 0. So just like the range has a lot to do with existence, null space has a lot to do with uniqueness. We always know that the 0 vector goes to 0. Linear combinations of 0 are always 0. Linear transformations of 0 are always 0. So it's not about whether there's the existence of a solution to this equation or the existence of a v is not an open question. The null space is never the empty set. But the null space could be as trivial as 0. If there's a unique solution to this equation, then it's just 0. But if the solution is not unique, then this makes up a higher dimensional subspace. And so the last topic at the beginning of this handout, or this section on the handout on page 5, is the rank, which is the dimension of the range space. So again, W could be something like 5-dimensional, but the range might end up being only 3-dimensional. Remember that the column space of a matrix, which is the same thing as the range space of that matrix, the space spanned by the columns does not have to be the same dimension as the number of columns that there were. There could have been dependencies among the columns. So the rank of a matrix is how many independent columns there are. The rank of a linear transformation is the dimension of the range space.